Okay, so welcome to this video. I'm going to take a look at something a little bit different today. I'm going to look at the idea of gradients and areas under graph in the mechanics part of the course. This is essential that when you're looking at a graph, you know what the properties on your graph, like your gradient, your area under it, your y-intercept, that kind of thing all mean. So let's take a look at a few things we're going to need to start with. So first of all, what do I mean by properties? So these are things like displacement, velocity, acceleration, stress, strain, all of those kind of things. And if we're going to be able to do this, there's a couple of things I need you better do. I need you better read. Hopefully that's okay. You've got a formula sheet, so you'll be able to look at what equations you need. And you'll also need to be able to rearrange your equations into y=mx+c format. So essentially what you're going to need to be able to do is make something the subject of your equation which is useful to you. Hopefully those things are both okay. So let's make a start with this. Okay, so let's start off looking at the first topic in materials, so density. So if we have a mass versus volume graph and we want to know what the density is, most of you will know density is mass divided by volume. But if you jump onto your equation sheet, you'll find this equation here for density here. So what we're going to do, rearrange it to y=mx+c format. So we've got mass on the y-axis, so we need to make m the subject of your equation, and therefore you can see the gradient of this graph would represent the density of the material there. So what we could do is measure change in y over change in x. We could get an idea of what the density of the material is there. So that's how we can use the gradient in this case to find density. So I guess the thing to, well, what if you don't know the equation of your graph? What if you've been given something random that you've not dealt with before? So when you're getting the gradient, what you're effectively doing is you're dividing your y by your x. So if you find the unit on your y-axis and the unit on your x-axis and divide them, you can kind of get an idea of what your gradient represents. So in this case, we know we've got kilograms divided by meters cubed, and you should recognize kilograms per meter cubed as the unit of density there. So that's another way you can look at this. The area under it, so for gradient we divided the two, so for the area under it, that's the graphical equivalent of multiplying your two axes. So essentially the area under this graph, so if we took this location here, we want the area here, we'd get by kilograms times meters cubed. Don't know if you have heard of that, but I certainly have never heard of a property with kilogram meters cubed as its unit. So that's basically telling you that the area under this graph is fairly meaningless and we're not going to use it for anything, which quite often turns out to be the case, but not always. So it's important to notice when they give you useful stuff. Okay, so that's the mass versus volume graph, and these are the general ideas of what's going on when we're getting the gradient or the area. So if we move on and have a look at Hooke's law, because both the gradient and the area are important in terms of Hooke's law. So this all comes from a graph. So what you should know is Hooke's law applies during the directly proportional section of the force versus extension graph. So it looks a bit like this. We've got force on the y-axis. So we want the equation with F as the subject, which it already is in your formula sheet. It looks like this, or sometimes delta L will be given as just be an x for extension. So we've already got it in y=mx+c form. So we can see that from this graph, the gradient is going to be the spring constant or the stiffness constant of the material there. That's fairly straightforward to see. If we look at the area, I'm going to use the units method to do this. So we can see we've got newtons and we've got meters here. So the area would have the unit of newtons times meters, or Newton meters, which you should hopefully recognise as a joule. So that tells us the area under a graph is some form of energy going on there. Because for the area we've multiplied a force by a displacement, that tells us the form of energy we've got is work done. So the area under this graph tells us the work you have to do to stretch a material to, say, this length here. So that's what that would tell you. And a lot of books will tell you that the area under here, or half Fx, is equal to the elastic potential energy. But that's not actually quite correct. The area is the work done to stretch the material, and what you assume is that that work done is 100% transferred into elastic potential energy. But that might not necessarily be the case. You might cause it to warm up, you might cause some plastic deformations in the material, both of which will transfer some energy not to elastic potential energy. So it's important to be aware of what's going on there. Okay, so that's your Hooke's law graph. Let's move on to a little bit more material stuff here. So if we look at stress, so we get this from a force versus area graph. And this is the equation you'll find in your formula sheet. Stress is force divided by the area perpendicular to the force. So we want force on the y-axis, so we want to make F the subject. So we can see that the gradient of this graph would be stress there, essentially. So that's how you can look at it graphically. In terms of the area under this graph, that would have the unit of newtons meters squared. Again, I've never heard of that. I've heard of newtons per meter squared, but newtons meter squared, I've never heard of that. If you have, please do let me know. But a bit of Googling and I did not find that anywhere. So again, the area is going to be fairly meaningless here. Strain, again, similar. So what we've got is a graph of change in length over original length. And again, we want to make the change in length the y, so then the gradient will be your strain here. And remember, that strain is actually unitless. So actually with the strain graph, units aren't going to be any help to you at all because everything ends up being unitless, like your gradient and stuff. The area under this looks quite promising because we've got a length times a length. So you've got meters squared, so it looks like it's telling you something about an area, but actually in this case it's pretty meaningless as well. The area under this graph doesn't tell you anything useful at all, really. Okay, so that's strain. So we put those two things together, we get Young modulus. And again, that's usually determined from the directly proportional section of a stress versus strain graph. And again, we rearrange stuff into y equals mx plus c format and realise that the Young modulus is the gradient of this graph. Again, the area looks promising. It's got a unit of newtons per meter squared, which could be a unit of pressure, it could be a stress, something like that. But actually, again, turns out to be fairly useless to us. It's important to be aware that quite often things we can calculate mean nothing. Okay, so let's look at this back with this graph though, because we can actually learn something about Young modulus from flipping it back to a force versus extension graph. So this is your general equation, and by substituting in the equations for stress and strain, we can get this equation here. And we want force to be the subject, so we just rearrange to make force the subject. And we find out something quite interesting, that from this graph, your gradient is the Young modulus times the area perpendicular to the force divided by the original length. So that gives us an idea of where a spring constant or a stiffness constant comes from. We know we can actually change those values by changing the Young modulus or changing the area or changing the length of your material there. So it gives you an idea of what the stiffness constant actually depends on by looking at it in this context, which is quite nice to have a look at. Right, so now we're going to move on and have a look at the motion part of mechanics. And a lot of the graph stuff here is to do with your displacement, velocity and acceleration graphs. So let's have a bit of an in-depth look at this. So suppose we want to know how much the velocity of an object changes between this time and this time here. So we've got an acceleration versus time graph. So hopefully you should be familiar with this equation, that acceleration is the change in velocity over change in time, generally speaking, over very small periods of time. So we can rearrange that to get the change in velocity with your value of acceleration times by time. So if your acceleration is constant, that's really easy. You just multiply your acceleration by the time. But from this, we can see acceleration isn't constant, so it's a little bit more complicated, and what you actually need is the area underneath the graph and between the graph and the x-axis here. This would represent now the change in velocity when the acceleration isn't a fixed value there. So that's what we can do, and that calculates the change in the velocity. So if we know what the velocity is here, and we calculate the change, we can work out what the velocity is at this point here, and this works regardless of whether acceleration is constant or not, which is the advantage of this method over using Suvat equations, for instance. Okay, so that's from an acceleration graph. So now we can move on to look at the velocity graph. Again, we're starting with the same equation. The acceleration is change in velocity of change in time. let's rearrange that slightly so we've got velocity in the position on its own, like this. And what we can see from that is that on your velocity time graph, the gradient is going to be the acceleration of your object here. And if your velocity time graph is a straight line, that tells you acceleration is a fixed value there. So that's one thing we can look at from a velocity time graph. The gradient is the acceleration of the object. Right, so the other thing we can determine from a velocity versus time graph is actually what the displacement of an object is between certain periods of time. So if we want to know, say, how far an object travels between this time here and this time here, what we can do is use the area of the graph to find that. So say, for instance, we knew when it was here, it had a displacement of 5 meters, and we know this area is 2 meters, like plus 2 meters, then that would tell us it would now be at a distance of 7 meters here. So we can see this all from a velocity time graph. Now, one thing I should point out at this point is that if your line is below the x-axis, you still want the area between your line and the x-axis here. So that's still the area that you want. But if it's below the x-axis, that's like a negative area. So in this case would be a negative change in displacement. So instead of going, I don't know, 2 meters more to the right and getting to 7 meters, it might be minus 2 and be 3 meters to the right, for instance. So direction is important here. Okay, so that's your velocity versus time graph. So I'm just going to finish off by doing something a little bit different. This isn't something you need to know, but it's quite interesting. So what we can do is we can use some calculus that you'll have learned about in A-level maths, specifically integration in this case. So we know that the change in velocity is the area under an acceleration graph. And finding the area under is using integration. So if we start at time 0, and then we go up to time t, and we integrate acceleration with respect to t, what we can end up with is this here, at. Now that only works if we assume that acceleration is constant, because then we just essentially did it like you would do with any constant integration, you just multiply it by t. However, in reality, sometimes acceleration is a function of time, which means this method doesn't work. So this is one of the reasons the Suvat equations are reliant on acceleration being constant. Okay, so we get this. So the change in velocity is going to be equal to at. If it started at u, ends up at v, that means v minus u is equal to at. And it might start to look familiar now because we can rearrange this into v equals u plus at. So we can use our integration to show that's true. We can do the same with one of the other equations here. So we know that the change in the displacement is the area under a velocity time graph. So if we integrate the velocity with respect to 0, between 0 and t, what we can do is replace that v with u plus at. The reason we do that is because we know v changes with time, so we want to replace it with stuff that doesn't. So we can replace v with u plus at, integrate that with respect to t, we get ut plus half at squared, and so the s in the Suvat equation actually stands for change in displacement of an object, so that's where the equation s equals ut plus half at squared comes from, using a bit of integration there. And then once you've got these two equations, you can just substitute them into each other and find the other Suvat equations there. Like I said before, not really part of the course, but quite interesting to see how you can use some of the skills in maths to determine some of the things that we use in physics. Okay, so that concludes this video on the different graphs in the materials and mechanics. I hope you found that interesting and useful. As always, please do let me know if you've noticed any problems with anything in this video, but thank you very much for watching.